What I'm going to do is touch on some points that have been raised by the other speakers, particularly Terry, Tarsila, Michelle, Tobias, but from a little bit of a different perspective and hopefully generate some discussion. So the main things I'm going to try to convince you of. The first point is a little strangely worded, and Madison cut me off from editing my talk. So basically, the point there is that you know most magma that's transported is intrusive, but those intrusions move gas, and so you know gas is really what comes out as the main job of volcanoes is to really transport gas, and if the magma comes out, that's sort of incidental. That's a strange point, a bit philosophical, but it's basically a point that intrusions matter. Second point I'm going to convince you of is that the volatile eruption cycle, and I'll sort of show you what I mean by that, is quite different from the volcanic eruption cycle, but that it's very important. We know this, and particularly eruption triggering and style of eruptions, the explosivity. I'm going to argue that ascent rate is a time-varying property, and that open and closed system is a variably defined and complex and time-varying property. And basically, this entire talk is kind of a not-so-subtle call for multidisciplinary time series of observations on decadal scales. So that's important. Okay, so we can learn a lot from global compilations from a multidisciplinary perspective about volatiles. And so this is just an example of the Dan Rasmussen's science paper. This was part of our funded GeoPRISMS project with Terry and Eric Howard, basically showing that volatile content controls magma storage depth when we look at sort of geophysical constraints on storage depth and then the magma water content. And so that's really great. So this also means that you can use geophysics to figure out what your magma water content should be, and that's a lot easier than polishing multiple. Another study recently that took a multidisciplinary perspective was this one from Popa that basically argues that explosivity is very strongly controlled by this narrow range of dissolved water content and a very narrow range of crystal content. And so this is the blue dots here. There's a very tight range of two conditions that basically determine explosive versus effusive. So that's quite interesting about volatiles and eruption styles. But what I'm going to do, again, I'm going to bring this back to time, is I'm going to go through a bunch of case studies and try to kind of synthesize them into those main points. And basically by looking at multidisciplinary case studies, time series of observations, what can we really say about volatile migration and storage, and what are the big open questions from taking this perspective? So I'll talk a bit about sort of the full eruption cycle, start of eruptions. Again, I'll come back to the intrusions and the importance of intrusions. And sorry, I know that petrologists hate intrusions because there's nothing for you to do with them. But I'll try to propose a solution at the end. I'll spend some time talking about what we observed during the ends of eruptions. And then hopefully, if I have time, I'll get into this sort of idea of open versus closed and some of the open questions and issues there. So the first thing I'm going to do is basically compare two case studies. And that's easy because at 2 points I can fit a line and convince you that there's something there. But really the reason it's two case studies is because it's very, very difficult to find this type of case study. So this comparison is based on this idea that Kathy Cashman and I put out a couple of years ago about top-down seismicity, and basically the issue that we see a mismatch often between the depth of the earliest seismicity for an eruption and really where the petrologists tell us the magma is coming from. And that kind of got us into thinking about, how does the magma sneak up to the depth where it starts to generate seismicity, and what does it imply about ascent rates? And again, my point about ascent rates being variable over time. So we came up with these little cartoons, and the main point here is they're mix and match. So they're not mutually exclusive. So that's the context for this. So I'm going to compare Mount St. Helens and Redoubt, again, 2 points to make a line. So they're very similar in some ways, very similar repose periods, sort of similar geochemistry to a geophysicist, they've got about the same as they do, but some interesting differences as well. So let's look at the data and see what we can say about these guys. So let me start with Mount St. Helens. So this is my favorite kind of plot. It's an earthquake time depth plot. So what you'll tend to see in all of these figures that I'm going to show are usually some kind of depth. It's all going to be in time, but here we're looking at earthquake depths. And so the little dots are the earthquakes. CDO's color codes are here. This is what the petrologists tell us where the magma was coming from. And the point here is that, this was a really kind of fast run of eruption, but it started very, very shallow. But the magma appears to have been ultimately sourced from something much deeper. And so we don't know how this snuck up here. From a gas perspective, the main point I want to make in both of these cases is that the 2004 eruption at St. Helens was a very flat magma, okay? It really didn't have a lot of gas when it erupted. So just kind of taking the long perspective view here, unfortunately, there's a big gap of data missing when we don't have gas emissions. But the main point is that compared to the 1980 to 86 eruption, both SO2 and CO2, there just really wasn't a whole lot. I mean, there's missing data, but I think this is a pretty common consensus about this eruption. It's flat magma. Okay, so that's weird. But I think the solution to this comes from kind of taking this larger scale time view. And again, this is a time depth plot of St. Helens. The reds are the eruptions, 80 to 86, 2004, 2008. This is one of my favorite figures in the world. Thanks to CBO for continuing to keep it going. And the thing I want to show you is here's that like really fast shallow run up. But if you look in between the eruption periods, you see these two swarms, and they're kind of over a broad depth range, reaching down to where we think petrologically the magma was stored, and then almost up to this very shallow kind of region here where the seismicity came up. And so we don't have a lot of gas data from these, but we're pretty sure these were intrusions. And so the idea here is that basically the magma that erupted in 2004 was really staged at a very shallow level and probably lost a lot of its gas. And so please, we're looking at gas emissions, and I know it's difficult through intereruptive cycles, and that's why it kind of came out so quick and so flat. We still don't know what actually triggered why even bothered to erupt. But okay, so there's Mount St. Helens. So in contrast, if you look at the 2009 eruption readout from kind of a similar perspective and time depth, don't worry about VTLP here. This was another kind of strange, and you'll see AVO's color codes here, very protracted run-up sequence that actually started with observations of some thermal anomalies, and some maybe weak seismic tremor, but suggesting stuff was already up here early on, and then kind of progressed into this, craziness, and then finally erupted. So when we look at the gas data from readouts, this is from Cindy Werner's stuff here on the left, we see that actually this was a pretty gassy eruption, pretty high in CO2, and also looking at tar cellulose thermal data, we see that there was a fairly long period of heating up. And so this is, again, very in contrast to Mount St. Helens. But when we zoom out and we take the sort of intereruptive cycle view, we see that there wasn't a whole lot that looks like intrusions going on in between readouts eruptive cycles. And so the fact that we had a long run-up, that we had a lot of gas, that this was kind of a deep gas signal potentially, that we weren't seeing a whole lot of very strong rock-breaking seismicity until later in the sequence, that we saw this long thermal anomaly, suggests that this magma did start ascending directly before the eruption, but did it kind of slowly. And again, there may have been other things, may have been some remnant magma from before, but this is kind of thought about ascent rates and the difference between the two. And then if you think about the explosivity of the two eruptions, St. Helens was not very explosive in 2004. It was this big long dome building thingy, but really very, very limited in explosivity. Readout was quite explosive. So maybe there's something also there in looking at this whole sort of what happens in between the eruptions and Where is the magma staged? When is the magma staged at shallow depth? How does that control how it loses its gas that feeds into the nature of explosivity? Okay, so let's test that. And again, it's really hard to find these case studies where there's an intrusion and then followed by an eruption and where we have a lot of data. So this is the kind of best third one I could find. And this is semi-Spokeshnoy in the Western Aleutians. Started erupting in 2018, and this is an old plot. This actually eruption is ongoing. So this is kind of a mid-grade, moderately explosive, again, very protracted eruption. What's cool about semi is that in 2014 and 2015, it had two swarms, very strong swarms, and remarkably very, very strong deformation. So this is a lot of uplift. So these were two very strong intrusions that happened, and then the thing decided to just hang out and then eventually started erupting in this sort of mid-level explosivity style of eruption. So the sources for the deformation are pretty deep. They're 6 to 8 kilometers. And we don't know a whole lot about gas in this one, but on Mount St. Helens end, we'd say, okay, intrusions before eruption, maybe it was, that's when it let off its gas, and it should be pretty flat when it starts to erupt. Read out, it didn't do that, so it was pretty gassy. So we don't have a ton of data from semi-Spokeshnoy. It's very remote on the gas emissions, but it actually has been emitting SO2. So AVO has been detecting with Traponi through the eruption, several good signals suggesting that it's still a pretty gassy magma. So the takeaway is that, maybe because this is a bit deeper, it still contains some of its gas from that intrusion that eventually fed the eruption. Maybe the time window between the intrusion and the eruption was only a couple of years in this case, compared to over a decade between intrusion and eruption at St. Helens, controls how much gas it can lead off during the intrusions. But I think there's something here. I mean, this is very arm-wavy, but my point is, I think there's really something here in considering what happens in between eruption cycles, not just what's happening right before, during, and after the eruption. So a plea for more kind of longer-term data sets, especially when we start to see intrusive activity, so that we can eventually connect it to the incident eruption. Okay, so I'm now going to shift to a little bit of a different topic, which is the end of eruptions. So we've put a lot of thought into the start of eruptions, and rightly so. And there's a little bit of a renaissance in thinking about the end of an eruption and both how do you tell that it's over and what's going on during the end of the eruption. So I want to highlight a few recent things that have happened during eruptions that ended. And so the first one is Ambro. Tobias showed some, this is had been one of the most prodigious gas emitters on Earth until 2018, when the eruption pretty much stopped quite abruptly. And so this is data from a lot going on, but the main thing I want you to take away from this one is that here's the time series of SO2 degassing, and this blue line here is a little sort of shift in the eruption that happened, and then the whole thing shut down, and you see that the SO2 basically goes off the cliff, gone. Okay, no more gas coming out. This is kind of, maybe in a sort of simplistic sense, what you'd expect the end of the eruption to look like. Okay, it's done. Gas is done. So you stop seeing gas. In contrast, however, we can look at Superior Hills. So this is a great figure that represents an inordinate amount of work by MVO. Again, another one of my favorite figures showing rates of earthquakes on the top, deformation proxies in the middle, and SO2 emissions in the bottom here over a very long time span. This is an incredibly valuable, rich observational data set. The eruption has had multiple phases, but it's basically hasn't done anything for over almost 12 years now in terms of surface output. But it's been a huge challenge because it's still inflating and it's still outputting gas. And so this is why, there's debate about whether this eruption is actually done or not, because these signals are ongoing. So very contrast to Ambrin, where the eruption finished at the surface, stop deforming, stop degassing. Here the seismicity turned off, which might be a little bit of a clue, but the point is that you can get a lot of gas volatile release following the ends of eruptions. So again, main point here is just there's a lot that goes on in terms of volatile movement and release when the volcano is not in eruption. And so really trying to collect these observations will help us to understand when if we're trying to account for the total volatile budget on Earth, the amount coming out of volcanoes, when is that happening, and how do we capture all of it? And so one thing that would be amazing to see is something like a volume time series at several of these volcanoes. Is the amount that's output during these intrusive events or these sort of post-eruption but still active, is it large compared to the eruption period if we can have a long-term perspective, or is it just kind of a small volume of what comes out during the eruption period? Okay, so the last end of eruption comes to this: how long do we have to look after an eruption? And so this is a study that blew all the seismologists' minds when it came out. So this is Aaron Weck's 2020 science paper on Mauna Kea. So why am I talking about Mauna Kea? Mauna Kea hasn't erupted for 4,000 years. Well, what's recently been discovered at Mauna Kea is this remarkable volcanoseismic pattern, something we call deep long period or DLP events. I won't get into what a DLP is and why you should care, except that they're very volcanic and they're deep. And what Aaron found is that when he looked very closely at continuous seismic data for Mauna Kea, he saw DLPs occurring in this incredibly regular repeating pattern. The periodicity would shift a little bit from time to time, but this was just this huge energy release in a very periodic sense of a very volcanic signal at depth. When they are located, they locate just above a low velocity zone, so base of the Moho. So suggesting that there's probably some residual melt down here. And he linked this to second boiling. And this is really the only explanation anybody could come up with, is why this regular pattern of this long period, and Darcy will explain a little bit, we tend to link those to gas release, long period seismicity over, ultimately he found, I think decades, a million plus of these things. And so his model is that this is Mauna Kea's residual chamber from 4,000 years ago, going through a second boiling, releasing volatiles, generating this periodic DLP signal today. So one thing we don't know here is this just something that's still residual degassing from whatever was going on 4,000 years ago, or have there been intrusions into the system since? So again, a plea to try to understand, has anything interesting happened at Mauna Kea in terms of new input to the magma storage region since its last eruption? And does that help us to explain this, or does this really tell us how long it takes for a magma chamber to bleed off its volatiles? Okay, next, final case study topic, and then I'll get into my not so subtle commercial for SC40. Everything. I want to just talk a bit about the idea of open versus closed systems. And I hear a lot, and maybe this is my geophysical misunderstanding, but I hear a lot of variable definitions of open, what it means for a volcano to be an open system, closed system. Some people say open vent, closed vent. And I think this is a question we should have some discussion around. So I'm trying to illustrate my point here with another long time series from Tolica volcano in Nicaragua. So Tolica is this weird little volcano that basically sits right on the cusp of erupting, and it does that as far as we can tell for decades. So it's really a classic open system, open vent volcano, and that it doesn't deform, but it's emitting a ton of gas, and it's producing a lot of seismicity. So we call it persistently restless. It occasionally does tip into eruptions. So what you're seeing on the top, this is a time series now of number of earthquakes, and here the frequency content matters. So the red ones are low low frequency or long periods. These are the ones that are kind of linked to gas, exciting resonance. And then the blues are high frequencies, so they're more like rock breaking. So they're when the system is stressed and having to push out on the rock. What we see is that when Talika is kind of in its just about to erupt state and very open, we're seeing a lot of these long period low frequency events. And then what it does before it erupts, I'm trying to figure out which one to show you that's best, is the LPs tend to, let's see what, tend to go down, and we start to see the emergence of the high frequencies. So what we think it does is it actually kind of transitions from open to closed, and that's what drives its rheatic eruptions. So we really, it's been a hard one to work with, so we don't see deformation, at least not on the scale we were able to measure with GPS. We do have some SO2 data, and this is contributions of probably several people in this room, a lot of folks over different time periods. And we see that it's got gas to it. It's not a ton, maybe that's not super impressive. We don't have a lot of data, but one interesting thing we see is that right before one of its explosions, and this was quite a significant explosive event in late 2015, actually Martin Moore was out there with a field school and took some measurements, and the SO2 was way down, and then right after the explosion shot way up. So our model here is that basically what happens at the system is that it kind of spends a lot of its time in this open state, bleeding off its gas, it's not deforming, generating a lot of LPs. And then our thinking is that actually that gas over time kind of precipitates and pushes it into something of a sealed state, where whatever's allowing that gas to bleed off kind of gets closed off, and then we start to see this shift into more rock-breaking events. We hope in the limited data we have, or we would at least hypothesize we would see the SO2 go down. And then it basically, that drives a rheatic explosion. We see that all of a sudden after the explosion, all of that accumulated gas come out, sharp SO2 spike, and then it kind of goes through cycles of this. So sometimes it's mostly an open system, but it goes through phases of closing, and that's actually what drives its eruption. So this is a complicated, this is the last paper we wrote, and this figure was, enough. And there's a lot more detail to it, but basically the plea is to sort of think about open versus closed system as a time-dependent, a time-varying state. That volcanoes can exist on different time scales in either open or closed. And I think this, so this is a really nice paper by Kevin Reed that came out a few years ago, actually, as a result of a Power Center collaboration. Looking at kind of the geophysicist idea of open versus closed, and maybe the more traditional gassing and thermal, and trying to put dots on the map. And you see that there's not a good match here, and there are also some weirdos here, and sort of some more complexity to semi-closed, closed, depending on what perspective you look at. So I think this is a topic that we should really think about a bit more. Just how do we define this? Because we know it's important. And then how does it vary in time? And how do we identify what state the volcano is at a given time? Okay, so I want to end with some open questions and then some potential solutions and opportunities. So I think, some of the questions that stand are really, pretty obvious. What's on the move? So this comes back to my angst. As a geophysicist, we kind of see stuff moving around, and we think, okay, maybe that's magma, or maybe that's fluid that's coming off the magma, but we really have a hard time telling what's actually generating the signal. We see earthquakes. Are the earthquakes because the rock is being pressed by magma, or is it because we're increasing pore pressures because we're fluxing more gas through and lowering the effect of normal stress on the fault? When are the volatiles and fluids on the move? This comes to these time series. We have these glimpses that volatiles are coming out in intereruptive periods, post-eruption, potentially over 1,000-year time scales. Yes, during the eruption, but also outside of the eruption period. And so I think this is really important, and it links into what the volcano really does. And then finally, how does the timing of the exsolution affect the nature of the ensuing eruption? So You know, that's the fun. We know that the gas is what controls the explosivity. So if we look at how much gas has been bled off and where the magnet is in space and time, we might be able to do a better job of anticipating farther out what an eruption might do in terms of explosivity, given its decades or centuries of past increased activity. Okay, next steps. Possible solutions. It's a volatiles workshop, so I can't finish without mentioning gravity. I'm a huge fan of gravity right now, gravity data. But I will say, having just gotten back from fieldwork in Chile, where we're trying to collect both gas and gravity data. Gravity data is maybe the only data set harder than gas emissions to collect. It is incredibly challenging, but it is incredibly valuable. And so I just want to sort of tease with this much older and incredibly heroic time series of campaign gravity measurements by Hazel Reimer and her colleagues from POAS that show you a nice gravity increase here, corresponding to a draining of POAS's lava lake and actually preceding an increase in SO2 sulfate concentration. I tend to mix and match. Just showing you the power of gravity to tell you that there is an intrusion occurring well before other things can reflect it, and really that it's actually magma that's moving up at a volcano that we know has a lot of gas circulation, has a big hydrothermal system that can generate. It's scrubbing a lot. It's potentially drying out. So are we seeing scrubbing being reversed? This is really the key that told us that during this period, this was new magma intruding. So gravity is amazing, but it's very hard to get. And I would invite you to read this fabulous review paper on the potential of gravity measurements on volcanoes and everything that has been done. I think this is the next big thing, and it's sort of volcano monitoring on long and short time scales. The technology has to improve. It's getting there. We're learning how to use instruments in campaigning continuous mode for much more than mapping, which is traditionally what gravity has done. It provides a lot of information. We do it in a time series. Okay. Next solution, and this is for the control. So what's on the move? That should have changed. That should be when are the volatiles moving? That top one. So my okay. When are the volatiles and fluids on the move? Okay. So crystal clocks. I told you intrusions clearly play a role, and so this is a plea and a cheer to all of you who are developing new crystal clocks to really tie them in. And Michelle made this point very well. She showed another GeoPRISMS funded study where we used crystal clocks as well as geophysical data to really figure out when magma was moving before an eruption and tying it to the geophysical data. But it would be great to extend this in time and to look on multiple time scales, using multiple crystal clocks, multiple measures in a given eruption. And my point here is kind of each eruption gets kind of maybe one or two or three or five. But let's think about the range of time scales and how we can use multiple diffusion chronometers to tie into geophysical data at multiple time scales. And I think this is exciting work. I know it's difficult. There's a lot of method development here, but this paper here, just to see the range of potential time scales now that we can get at is incredibly exciting. Okay, I'll sum it up. Next steps, how does the timing of exvolution and so many other questions. Really what we need are these decadal scale multidisciplinary observation time series. And so I'm stealing this slide from Terry's talk. This is one of the things we would like to do in the MDE component of SC4D. We would like to instrument, say, 30 volcanoes on a decade-long scale with multiple types of instruments and essentially test these hypotheses in a controlled manner from volcano to volcano, looking through the entire eruption cycle. So, bulk array. What does this need to look like for this to work? This is the point. Like, we should discuss this, make sure it's right. So I'm already kind of starting to add things to the list here. Terracula is an amazing satellite thermal time series. We need those. We need other satellite time series data. We need maybe campaign or continuous gravity, which is not on this list. This is something we should be thinking about. What do we want our multidisciplinary observations to look like on this time scale so that we can understand when are volatiles moving, how do they control the eruption style? This is one of our primary questions. Here it's composition, but I think we're also talking about volumes, flux, and much more than composition. We know that this affects eruption, both precursors and eruption styles. So let's collect the data that really helps us dig into that.